Hello and welcome to this video on how to go from linear physics to rotational physics. What we mean by that is really a simple mapping that enables you to take all the equations governing linear kinematics and even linear dynamics and turn them into stuff that's actually talking about rotational motion. So this is really that simple. Once you know linear kinematics and or linear dynamics, then you know almost everything there is to know about rotational kinematics and dynamics. There's only a few subtle differences. And the reason that that works is basically there's just a simple mapping to go from one to the other. So let's take a look at that real quick and then highlight the extra bits of information that you need in order to have it all make sense. So the mapping is quite simple. In linear kinematics, there is a variable that describes your location, one that describes your speed, your velocity really, it's a vector, your acceleration vector, and then there's a couple of things that come in once you start thinking about dynamics, which are things like the force vector, the mass of the object, and even potentially linear momentum. And then how does that turn into angular things? Well, in terms of angular motion, if you're rotating, then you need to describe an angular position, an angular velocity, angular acceleration, the angular equivalent of force, which is torque, the angular equivalent of mass, which is the moment of inertia of the object, and indeed there's an angular momentum. And if you just make these simple substitutions, that you take whatever was talking about a linear position and now make it talk about an angular position, and similarly with all the other variables, so force becomes a torque, etc., then all those equations actually hold. So the equations for linear motion of constant acceleration can easily be turned into the equations of motion for constant angular acceleration just by doing this remapping of symbols. But there are some differences because, of course, these angular quantities are still the things that were vectors originally are still vectors, and we need to be able to assign a direction, for instance, so that's going to complicate things. But even just thinking about our angular position might at first be a little bit odd, because the angular position, of course, is just going to be cyclic now. If you're talking about going around and around and around in a circle, well, you realize that those coordinates really just go from 0 to 360 degrees. Now, for our purposes, you often want to know actually how many times have you gone around. So in fact, even though it's an angle, we do tend to talk about it as being greater than 360 degrees if you've gone around more than once. And so there's some subtleties there, and there's further subtleties in talking about this angular position, because you may just actually like to talk about how many times you've gone around. So you can specify theta as not only in degrees or radians, so angular proper angles, but you can also just say, oh, well, I have in fact made 1 1/4 revolutions. By the same token, all the other things that have units of angle per unit time or angle per unit time squared, etc., can also be expressed either as degrees, radians, or even revolutions per whatever time unit is required. So omega, for instance, as an angular velocity, can be described simply in terms of radians per second, say, or equally well as revolutions per second, or even, of course, revolutions per hour. So that's one of the main subtleties that arises, is this weird way in which we're describing the angular position. But we really just mean, you pick some reference point, and then you just tell me the angle, and I know that I've just gone that angle around some circle. Okay? Because all the motion is circular, so it doesn't make sense for me to try to talk about any sort of linear distance that's just constantly increasing, etc. And the other thing with this is, how do you figure out the direction of these vectors? You might be tempted to say, for angular velocity, for instance, that you'll take it to be the same direction as that tangential velocity that you know is associated with the angular motion. But in that case, that's always changing, which is not really something that we would like to think about if we're talking about actually just nicely uniformly rotating, like a hand on a clock or something. That's going at a steady rate. We don't really want to say that omega is constantly changing for a clock hand moving smoothly around the clock. So what can we actually do? So what we can do is introduce some right-hand rules for torque and for angular momentum, but those come because both of those are calculated as cross products. Or you can actually think there are related to alpha and omega, respectively, in which case they're just inheriting their direction from those vectors. So in summary, what we've seen is that indeed rotational and linear physics are very much the same. All you have to do is change the symbols according to that simple mapping, and the physics will in fact work.